So today we'll be taking a look at what is called the hyperbolic functions. Now I have to say this section, maybe more than any other section, is full of so many formulas. It's like more formulas in one section I've ever seen in any one section of calculus. But the good news is I will give you all of those formulas. There's nothing here you have to memorize. Just try to understand the process. And so, but if you need a formula, I will be providing it to you on the test. Okay? And this section is not going to have a lot of high emphasis on the final. We might have like maybe one or at most two questions. And the formulas will be right next to it. And it's a little bit of an obscure section in the sense you don't see this very often. However, every once in a while, like in higher levels of math, such as differential equations, Professor Bulwer tells me the students need to know this, so make sure you cover this in Calc 1. And I don't have time every year to do this because sometimes we have a holiday fall on a Tuesday, Thursday class. But this semester we have the luxury, we have one extra day, and we're going to try to do a good job going over this material. Hopefully you'll be glad you did it when you get to the FQ, if you get that far. Okay, if nothing else, so even if you're not going to get that far in itself, it's going to give you some nice analytical techniques today. We're going to do some proofs. You're going to basically strengthen your skills about dealing with trigonometric functions. You're going to strengthen your skills about dealing with exponential functions. So it's kind of good practice. And even if you never use this again, it also reviews all of Calc 1 in a sense. So in that regard, it's a good review of what we've done so far in Calculus 1. Okay, first of all, we define what these functions are. So sine hyperbolic of x is defined to be, as you can see, it's a combination of exponential functions. So even though it's called sine or hyperbolic sine of x, it really has nothing to do with the sine function. It is really an exponential function, and the definition is e to the x minus e to the negative x all over 2. And the hyperbolic cosine function is defined as e to the x plus e to the negative x divided by 2. As you can see, the main difference is the plus or minus sign. The hyperbolic cosine has a plus sign in the middle, and hyperbolic sine has a minus sign in the middle. Again, you don't have to memorize these formulas, but just be familiar with them as we're going to be using them a lot in today's lesson. So once again, I'm going to emphasize hyperbolic sine and hyperbolic cosine have nothing to do with trig functions. They are really exponential functions of some form. Why do they then have this weird name, hyperbolic sine? It has nothing to do with a trigonometric function. Well, as it turns out, and as we're going to be able to show today, when you deal with these exponential functions, they exhibit properties similar to the trig function. So for example, in trigonometry, what do we have? Sine squared plus cosine squared equals what in trigonometry? Equals 1, right? Here, what you have is you're going to have, and that's probably one of the first identities that I will show you. You will have cosine squared minus sine squared equals to 1. In just a little bit, I'm going to show you that identity. For example, you have double angle identities in sine, say sine 2x is 2 sine x and cosine x. Well, we have something very similar here for hyperbolic functions. So even though these are exponential functions, they exhibit properties similar to trigonometric functions. I guess that's why they gave this weird name, hyperbolic sine and hyperbolic cosine, even though they're really exponential functions. Okay, a few other simple rules that we should know, just like trigonometric functions. Okay, so these are identities just like trigonometric identities, as you can see. For example, hyperbolic tangent is defined to be hyperbolic sine over hyperbolic cosine. Basically, all these 6 functions are defined very much like the regular trig functions. For example, hyperbolic secant is 1 over hyperbolic cosine, and so forth. Cotangent hyperbolic is inverse of tangent hyperbolic, etc. So the only 2 that are different are the first 2, right? Sine hyperbolic is defined as an exponential function, and cosine hyperbolic defined as an exponential function. Okay. Now, let me also try to tell you, like, where we're headed. Like, by the end of today's class, we're going to be able to do something as follows. We're going to be able to integrate, because after all, we're in calculus, and, why are we all of a sudden, going on tangents doing hyperbolic functions? Well, they're going to help us do some integrals. For example, this integral right here, dx over the square root of 1 plus x squared. Can you do this one with u sub? No, there's no x on the top. Is this inverse sine function? Well, if you had 1 minus x squared on the bottom, that would have been inverse sine, right? But it's not. So this has a little bit of variation. It cannot be done with anything we've learned today. Well, it will turn out that this one can be done with hyperbolic inverse sine of x. So who would have thought, all of a sudden this weird function that has exponentials will give us the answer to an interesting integral question. Or also, for example, another thing we're going to be able to see at the end of the class today is if you're trying to integrate something like this, 1 minus x squared on the bottom. Well, if it was a 1 plus x squared, what could you have used if it was 1 plus x squared? Inverse tangent would work, right? Here, inverse tangent doesn't work. U sub doesn't work. Any guesses what might work here? Now that we're talking about these hyperbolic functions? Take a wild guess. Tangent hyperbolic is going to work, or hyperbolic tangent inverse. So tan h inverse of x is going to work. So this is why, again, they have such similar names, because they exhibit such similar properties with their counterparts in trigonometry. Okay, so we're going to come back to that near the end of the class today. Okay, so these are the definitions of the 6 hyperbolic trigonometric functions. From here, we're going to be able to, first of all, look at some properties. Okay, so these 3 properties, first of all, look at on the right column the trigonometric identities, and on the left column the hyperbolic function identities. As you can see, they're very, very similar, except the first and the third has a minus instead of a plus. So for example, we know that cosine squared plus sine squared is 1, right, in trigonometry. In hyperbolic world, cosine squared minus sine squared hyperbolic is equal to 1. In trigonometry, we know a double angle identity for sine 2x. There's a very similar one, as you can see on the left column, for hyperbolic sine. And we know this identity, 1 plus tangent squared is secant squared. We've used it in the past, right? For hyperbolic functions, again, you have 1 minus hyperbolic tangent squared equals secant, hyperbolic secant squared. So there are very similar properties. We're going to show like 1 or 2 of those. Okay, so let's start, for example, trying to show the first one, hyperbolic cosine squared minus hyperbolic sine squared equals to 1. Let's try to show that. And again, it may be a little bit intimidating, all these formulas today, but please remember, you don't have to memorize any of them. Like if I said to you, show that hyperbolic cosine squared minus hyperbolic sine squared equals to 1 on the test, right next to it I would give you, what is the definition of hyperbolic cosine? Which we just saw on the top of the page, right? I'm going to go back there for a minute. I would give you right away the definition of hyperbolic cosine and the definition for hyperbolic sine. So you would have those formulas right next to you, so that, let's see, why is it not erasing it? Because I had my magic marker, which is temporary, I guess, that it erases by itself. Okay, so we're going to prove one of these. Or maybe we might even do all of them. We'll see. Okay, starting with the first one. First of all, what should I write? So we're trying to show that this is equal to 1. What should I write for cosine hyperbolic squared? What was the definition for hyperbolic cosine of x? Look to the, if you don't write that many formulas today, because I'll give you this in a sheet of, later on, but at least you should write the first 2. So like you should definitely write down the definitions of sine and cosine hyperbolic. Make sure you have these on your sheet so you can refer back to it over and over today. Okay, so with that understanding, those are our basic definitions that we're going to be using. What can you tell me for cosine hyperbolic squared? What is cosine hyperbolic, by the way? Good. Minus, okay, we want to square that, minus hyperbolic sine, which is very similar, right? This has one difference. What was the difference for hyperbolic sine? It has a minus in the middle, exactly. Okay. And I'm squaring them because that's what the left-hand side was, right? Okay, so we're going to be simplifying this. So basically, this is like a practice problem in algebra, right? How do you simplify a binomial or things like that? Well, this is really the top squared over the bottom squared, right? The bottom squared is going to be fourth. So to simplify things a little bit, this is how I'm going to do it. I'm going to put 1/4 up front, because when you square the first and the second, they will both have a 1/4 in the denominator or 4 on the bottom. So I pull that out as 1/4. Now what I need to write is, what is quantity e to the x plus e to the negative x quantity squared? What is this? Let's write it out in the brackets here. Okay, square the first term. What is e to the x to the second power? Now, when you have the power of a power, good review of algebra, what should we have? You multiply the powers, right? So it will be e to the 2x. That's the first term squared. Then the second term will be 2 times the first and the second. The first is e to the x. The second one is e to the negative x. And the last one should be what, when you square this one? E to the negative 2x. Once again, power of a power, you multiply the powers. Okay, minus the remaining ones I'm going to put in parentheses. But don't forget to distribute my negative sign. Okay, now we're distributing this, that binomial over there. Okay, so once again, what is the square of e to the x? E to the 2x. Then you have minus 2 times the first and the second. Why minus? Because this one had a minus in the middle, right? The binomial had a minus sign in the middle. And what about the last one? The last one is always going to be plus, right? Because it's the last one squared. And that will be e to the negative 2x. Okay, now there should be a lot of cancellations. I'm going to go ahead and distribute my negative sign. By the way, what is e to the x times e to the negative x? It's e to the 0, which is 1, right? So that will be, but there's a 2 in front of it, so negative times negative is positive 2 in that case. And then the last one will be negative e to the negative 2x. Got to be really careful with the signs here. So up front we had e to the x plus 2 e to the x to the negative x. Once again, that is 1. We get plus 2. And e to the negative 2x. Okay, let's see if we see any cancellations here. Oh yeah, that's e to the 2x. Okay. So any cancellations? Right, the e to the 2x and minus e to the 2x, they'll cancel. The e to the negative 2x with minus e to the negative 2x, they cancel. So we are inside the brackets. All we have left is 2 plus 2 or 4. But remember that there was a 1/4 outside of everything. So this will be 1/4 times 4, which is 1, right? And what were we trying to show? We're trying to prove the first identity here, right? Which is cosine square h minus sine square h equals 1. We're trying to show this one. And we've done exactly that. We started with the left-hand side, and we show that that left-hand side is equal to 1. Okay. I'm going to have you guys work on number 2. On this one, we're going to try to show that hyperbolic sine of 2x is, so let's say proof of number 2. So we're going to try to show that hyperbolic sine of 2x is 2 times hyperbolic sine of x times hyperbolic cosine of x. And my suggestion to you is start with the right-hand side. Start writing out what the right-hand side is and simplify. See if you can get the left-hand side. In the meantime, I'll give you some time. So we start with the right-hand side. Write out the definitions. One of the 2's on the top and one of the 2's on the bottom will cancel. So we have only a half that can be factored outside. And then you have to multiply these two binomials, right? E to the x minus e to the negative x multiplied with e to the x plus e to the negative x. Now you can use the FOIL method, of course, here. Or you can notice that this is like of the form a minus b times a plus b. And what do we know about that? It's the difference of two squares. That is a squared minus b squared, right? Because negative ab and plus ab, those are going to cancel. So in this case, how would you write that? What is a squared? E to the x to the second power. And we just went over that, right? Power for power is the product of the powers. This is e to the 2x minus, exactly, e to the negative 2x. Now, we're trying to show that this is equal to the left-hand side. First, there's a question. Yes, Daniel?
How does that work? Square root
what do you mean square root? There is no square root there, though.
Well, I mean, like, with the difference of square. Square root of a minus square root of b times square root of a.
Okay, but does this look like the left-hand side? We're supposed to show this is equal to sine hyperbolic of 2x. Does it really look like that? Well, let's think about it. What was, once again, sine hyperbolic or hyperbolic sine of x? It was e to the x minus e to the negative x divided by 2, right? So what do you think is hyperbolic sine of 2x? You would have to replace every x by 2x, right? If you do that, you get sine hyperbolic of 2x. Do we have that here? Because you can look at it like this. This is the same as e to 2x minus e to the negative 2x divided by 2, right? And this is indeed the hyperbolic sine function with 2x plugged in for x. Does everybody see that? This is the same as hyperbolic sine function of 2x. Because instead of x, they plugged in 2x. So we have proved. We start with the right-hand side. We end up with the left-hand side. So we've proven that identity as well. OK, we're going to prove also the last one. But the last one, we're going to prove it in an easier way. Now that you have ideas about the inverse, rather hyperbolic sine and hyperbolic cosine, let's also prove that third identity, which was, the third identity was 1 minus hyperbolic tangent square is hyperbolic secant square. So let's also prove that identity. So this will be proof of number 3. Right, where we're going to try to show that 1 minus hyperbolic tangent square is equal to hyperbolic secant square. Now, we could do this from scratch. From scratch meaning, we could try to determine, like start from the left-hand side. How could you possibly determine a formula for a hyperbolic tangent function? Any thoughts? Yes, Madeline?
I think that the short way instead, I take the original cosine hyperbolic square x minus sine hyperbolic square x equals 1. I divide everything by
Exactly. The same way you would have proven it using the regular identity, 1 plus tangent square equals secant square in the real trigonometric world. Yes, you can do it that way. But if you want to do it the long way would be like to try to get tangent hyperbolic in terms of its definition, in terms of e to the x. How could you get hyperbolic tangent in terms of e to the x? Any thoughts? You know sine hyperbolic in terms of e to the x, right? You know cosine hyperbolic in terms of e to the x. So how could you get hyperbolic tangent in terms of e to the x? You could take the ratio of 1 over the other. So like the sine hyperbolic has this in it. Over 2, right? Over cosine hyperbolic has this in it. So if you're dividing two fractions, you would multiply, invert, and multiply with the top. So this bottom can be transposed on the top as, you can multiply it with the top. and the 2's cancel. So you have for yourself the definition of hyperbolic tangent function. So it is possible to do the question using this definition, but it would be very long. You know, you have to square it, you have to do 1 minus to it, and try to show on the right-hand side. It could be very tedious. Instead, the easier way is a method, pretty much what Madeline was describing earlier, that is, try to use those 6 identities I gave you at the beginning of the class today, the 6 identities about basically these 6 identities, or any one that is applicable in this case, like tangent hyperbolic is sine over cosine hyperbolic. So using those, let's see, where was I? Okay. So instead of tangent hyperbolic, using those properties I gave you at the top of the first page, what can you tell me for hyperbolic tangent function? Exactly, that's hyperbolic sine, but this is only squared, so this has to be squared over hyperbolic cosine. So I'm starting with the left-hand side, and I'm going to try to show that this is equal to the right-hand side. Okay, how can I combine these 2 fractions? Get a common denominator, multiply the top and the bottom of the first one by what? By cosine hyperbolic square. Then they're going to have 1 common denominator. Which is hyperbolic cosine square on the bottom. Okay, and what do we know about this first identity, the top basically? That was formula number 1, 2, or 3. Let's go back. That was number 1, right, from this list? Right here, that was number 1. And we know that cosine hyperbolic square minus sine hyperbolic square equals to 1. So I'm going to put that in our equation as 1. And on the bottom, we have hyperbolic cosine square of x. And guess what? What is 1 over hyperbolic cosine square? That will be hyperbolic secant square. Yes. Basically, this top and this bottom were multiplied by cosine hyperbolic squared. Because we want to get common denominators there, right? Basically, when I put an identity, usually I start with the left-hand side or the right-hand side, just one side though. And I work my way until I end up with the other side. So in this case, I started with the left-hand side. I said left-hand side equals to this. Then I got common denominators. Going from this step to that step, what I did was I got common denominators. Exactly. Instead of 1, basically, I use cosine square hyperbolic over cosine square hyperbolic. If you like, let me write out that step for you. So 1 is the same thing as this, correct? This is the same thing as 1, right? And then second piece was this. Right, so now I have common denominators, so I can write it like this. And from there, we use the identity to get a 1 for the top, and then the ratio was hyperbolic secant squared. So we also proved the third identity. Okay. Okay, now we're going to take a look at the derivatives of hyperbolic trig functions. And once again, they have very similar properties to that of trigonometric functions, except they're a little bit easier to remember because there are no negative signs to mess up with. Okay? So normally, what do we know about the derivative of the regular sine function? The regular sine function is cosine, right? In the hyperbolic world, the derivative of hyperbolic sine is hyperbolic cosine. Okay? But the second one is a little bit surprising, right? The derivative of hyperbolic cosine, what is the result in the regular trigonometric world? It's negative sine, right? But in the hyperbolic world, there is no negative to worry about within derivatives. So it makes things even easier for us. And the derivative of hyperbolic tangent is hyperbolic secant square. Again, very similar formula. That one is identical to its counterpart in trigonometry. And we're going to prove only one of them, because if you can prove one, you can prove all the other ones with the same technique. We're going to prove that the derivative of the hyperbolic sine function is hyperbolic cosine function. Any thoughts about how we could start proving something like this? We're going to show the derivative of hyperbolic sine is hyperbolic cosine. So I start with the left-hand side, the derivative of hyperbolic sine. So what should I be doing next? What should I be putting here? What was the definition of the hyperbolic sine? What was the definition? Yes, Christine, go ahead, put this. E to the x, hyperbolic sine has a minus in the middle, right? And then e to the negative x over 2. We want to take the derivative of this. Well, this is like taking the derivative of an exponential function. We've done that, right? So let's go like a piece at a time. Because the bottom is just a constant, I can take that outside. So this is like 1/2 times the derivative of e to the x minus e to the negative x. Okay. So now 1/2 remains. Who can tell me the derivative of e to the x? Again, it's good review for the final exam, because in the final we're going to deal with the differentiation again, right? So we're remembering once again, what is the derivative of exponential function? Itself times the derivative of the power, but the derivative of the power here is 1, so it doesn't even matter. But what about the second part, if you differentiate this one? E to the, right, positive e to the negative x. The reason is, first think about this one. What is the derivative of e to the negative x? The derivative is e to the negative x times -1, right? It's like e to the kx. It's like e to the kx times k in differentiation. In integration, it was divided by that constant, right? So for this question, it's times -1. But because there was another minus in the middle, I'll make it a positive e to the negative x. And guess what? What does this look to you like? This is the definition of which function that we learned today? Hyperbolic cosine. So this is the same thing as hyperbolic cosine of x. So we've proven the first one, and I'm not going to do the other ones, but once again, you can start by the definition of hyperbolic functions and prove the other ones as well. Okay. Okay, next we're going to take a look at inverse hyperbolic functions. Once again, first let me state the formulas, but as I've been doing all along today, once I write the formulas, at least for one of them, I want to show you a demonstration. Where did they come up with it? Because usually there's a good explanation. These formulas don't just fall, with parachutes from the sky. There is a reason why the left-hand side is equal to the right-hand side. Something interesting to notice is in inverse hyperbolic trig functions, if you look at the right-hand side, they all end up having ln, or the natural log function. Now, does that make any sense? Because think about it. The regular functions, the hyperbolic functions, are technically exponential functions, right? So does it make sense that their inverses have natural logs in them? Right, because again, the original functions are defined in terms of exponentials, in hyperbolic sine, hyperbolic cosine. So their inverses have natural logs in them. So to me, that makes sense, because the inverse function of the exponential function is the natural log function. But they look very weird and complicated, like this natural log of x plus the square root of x squared plus 1. Where did all of this come from? We're going to take a look at that in just a moment. So I'll just do the derivation of the first one. That's a derivation of equation 1. I don't have to rewrite it all over again. Okay. Okay, in order to be able to derive this one, we have to dig back into some knowledge we learned in college algebra and pre-calculus. Let me see how many of you guys remember how to find an inverse function. Let's say you have y equals, just this is a general question about how do you find an inverse function of, let's say, something like this. How do you find it? Does anybody remember from college algebra? Yes, Mike? First you switch x and y, and then you solve for y. That's exactly right. Basically, there's actually another way to do it. Basically, here you know y in terms of x, right? To find the inverse function, technically what you really want is you want to solve x in terms of y, but then by switching these variables, we ensure that your final answer will come as a function of x, because that's what we're usually used to. But the bottom line, when you find inverse functions, if you know y equals this, if you solve for x here, technically you're going to have an inverse function, but it's going to be in terms of y variable. To get rid of that complication, that's why we have this interchange the variables as your first step. But basically, what is an inverse function? If you think about it, you know a function that goes from this set to that set. Inverse function goes the opposite direction, right? It goes from the other set, from the y's into the x's, basically. Okay, so how do we prove the first one? We're going to use this idea from algebra. So start with the definition of the hyperbolic sine function. So we know that hyperbolic sine function is, as you can see, everything goes back to the definition, which is e to the x minus e to the negative x divided by 2, correct? Now let's call this y equals. So basically, if we could solve for x right now, we would be done. So then, because you know x in terms of y, that would give you the inverse function. But we're going to do this little intermediate step that they always teach in college algebra. They say first interchange the variables. This is just a cosmetic thing. It really, you could have solved the problem without doing that. But everything would be like this answer will come out in terms of y if you did not do this next step. Okay. So just for the cosmetic reason, we're going to do that step. So interchange x and y. Okay, then we need to solve for y. We need to solve this equation for y. Let me first get rid of that 2 on the bottom, multiply both sides by 2. Okay, so we're getting this. The goal is we need to solve for y. If we could do that, we're going to have, supposedly, this answer right here, the inverse function of the hyperbolic sine. So once again, how are we proving the inverse hyperbolic sine? We start with a regular function, and then we're trying to find the inverse function. To find inverse function, we interchange the variables and solve for y. Now, this equation in itself is a very complicated equation. It's not easy to solve for y. You could try it, I worked on this, and it's not very easy. And the easiest way to go about it is, before I say it actually, give me some thoughts. If you want to solve this for y, what would you do? Yes, Daniel? You're going to have to bring in natural log somehow, right? Because you have an e to the y. Somehow we're going to have to bring in natural log. But if you bring it right now, if you apply ln to both sides right now, you'll be stuck, because what is this quantity? The natural log of e to the y minus e to the negative y. There's no way to simplify that because there's a minus in the middle. So you cannot bring it just yet. But you are at one point, we're going to have to bring in the natural log function. So here's a little trick that I'm going to apply. And most books, they don't show you this because I guess it gets a little bit messy. But I know you guys are good, and you're going to be able to follow this. So here's what we're going to do. We're going to use substitution. Again, something you probably learned also in algebra. To solve an equation, if something repeats itself, you can do a substitution. Let u be equal to e to the y. Then I'm going to rewrite the same equation again. So 2x equals, what should I write on the right-hand side? U minus 1 over u. Because what is e to the negative y? E to the negative y is the same as e to the y to the minus 1 power, right? So which is the same as u to the minus 1. So you could say u to the minus 1, or you could say 1 over u for this. Okay. So if we could solve for u now, then we can come back and solve for y. That won't be such a big problem. But how do you solve for u? Any thoughts? This is again, it became an algebra question right now. How do we solve for u here? Let's get common denominators. Always a good idea. Or eliminate the denominator. Since it's an equation, let's multiply both sides by what? By u. So multiply this side by u and multiply this side by u. So then I have 2ux equals u times u, which is u squared, minus u times 1 over u, which is 1. And I'm going to put everything on the same side. Anytime I see a quadratic function, I want to write it in the standard format like this. Okay. To solve a quadratic equation, once again, we're going back to algebra. Usually, what do you do? First try, what do you try first? If you have a quadratic equation, first you try to factor it, right? But this one looks like it's going to be a tough nut to crack. With a factoring, there's a u, there's an x, right? It's going to be very hard to factor this one, right? So what do you do next if you cannot factor something easily? You go to the quadratic formula, right? So that's what we're going to do here. But remember, here the unknown is which variable here? Which one we're trying to solve for right now? We're trying to solve for, well, look at what I wrote earlier. I said solve for y. But then we did a substitution. Now we know u in terms of y, right? So what do you think we should solve for here? We should solve for u. Yes, we should solve for u. And if we're solving for x, actually, it would be so easy because it's up there. X, you just divide both sides by 2, right? X would have been very easy to solve. So we're going to solve for u. From there, we're going to get our y. OK, so solve for u. Let's apply the quadratic formula. U equals negative of b. OK, what is my negative of b here? Actually, let's do this. First, write down a, b, c on the side here. What is a? 1. What is b? Remember, u is your variable. If u is your variable, b is everything surrounding your u, which is negative 2x, right? And what is your c? Negative 1. OK, now we want to have negative of b, according to the formula, which will be, let me remind everybody the formula. Negative b plus or minus square root of b squared minus 4ac all over 2a. This is the formula. OK, so negative of b, which will be 2x, plus or minus the square root of b squared, which is, if you square this quantity together, what do you get? 4x squared. And the formula states, then do minus 4ac. So I have my minus there. I'm going to do 4, a is 1, c is negative 1. Everything should be divided by what? 2a. In this case, that's just 2. Let's simplify this. We're actually almost there, believe it or not. I see a simplification here. Let me see if you guys see that as well. For example, that 4 under the radical, could I factor it and take it out? Because I can factor the 4 from both terms, then I can take the 4 out as what? As a 2, exactly. And then everything will have a 2. There's a 2x, the squared will have a 2 in front, and there's a 2 on the bottom. So you can further factor the 2 out and cancel the 2's as well. So that will leave us with the following. OK, so first let me write the first step. This is plus or minus 2 times the square root of. Again, did everybody understand how I factored this 2 here? Inside the square root, I took the 4, and then you extract the 4 outside the square root as a 2. And I'm going to take a 2 from both terms on the top, because I want to cancel that with the 2 on the bottom. So we have something here. We have this. But what were we really trying to solve for here? This is u equals. U is equal to this. But we didn't really want u. What do we want? We wanted, I even wrote it up there for you. We want to solve for y to get the inverse function. Well, we know the following. U is e to the y. U is e to the y. Okay. what do you think y would be? If u is e to the y, what is y then? Forget about the previous line right now. Just look at the simple equation. If u is e to the y, then what is y? Exactly, natural log of u. If you apply natural log to both sides, you get ln u is equal to y. So to solve for y, what are we going to do to this? If u is equal to this, and I'm trying to get what y is, y will be equal to what? According to this line here, it says y should be natural log of u. And u is this, right? So what should I be doing? Take the natural log of everything. So basically the answer will be natural log of x. Okay, I'm only going to write the one with the plus, and I'll tell you why. Because if you write the one with the minus, this will be negative. Because this quantity is greater than x, and x minus it's something greater than x, that will be negative. That won't make the natural log defined, so you can only take the one with the positive. And what we got is the inverse function for the hyperbolic sine. A lot of work, but let's check back with that formula, the inverse function for hyperbolic sine. Did we get it? I heard it's close. What do you mean? After all that work, it's just close and not exact? Let's double check. It has to be exact. It's exactly the same thing, right? I just maybe wrote it one on the left, one on the right. Okay, but again, the point is, anytime you see a formula out there, usually there's a really good reason why there's that formula. If you go into the theory behind it, you can see what that formula is. And I was reading a book recently. It's called, I think, The 5 Equations That Changed the World. I may have changed the title a little bit, but something of that nature. And the author was describing an equation as basically an equation in mathematics as poetry, because there's so much information packed into that tiny little line there. All the information, just like in poetry, just a few words can describe such a complicated, interesting situation. So I thought that was very interesting. And again, this example reminds me of that, because there's so much information packed into that one little line there. Okay, so you don't have to memorize these inverse hyperbolic functions, but if you need to, you'll be provided them. And every once in a while, I might, on the final exam, I might either ask you, show that type of a question. But I'm not going to pick the longest ones, obviously. Some of them I'm just showing you so that you understand, where the formulas are coming from. Okay, let's see. What else do we have? Okay, so far, let's just recap what we've done. We got familiar with the hyperbolic trig functions. We proved a few identities. And we've looked at their inverses. Okay, so far, this is what we've done. We also have looked at their derivatives, right? The derivatives of the hyperbolic functions. Any guesses what we're going to do next? So, yes, something to do with integrals, and we just did the inverse functions, right? So we also are going to do the derivatives of the inverse functions. Now you see what I meant. This section is like, it has so many formulas in it. I almost feel bad covering it in one day, but usually it's covered in one day. And the reason being, it's not the most essential section in calculus. That's why they pack everything in one day, saying, okay, in case you need this in the future, here's everything you ever need to know about hyperbolic functions. Okay, I think I'm going to